This problem asks us to determine the total average power supplied to the load in this circuit. Because the series impedance of the inductor and capacitor are equal in magnitude and opposite in sign, from the standpoint of calculating average power, the network can be reduced to that shown here. An impedance of 0 ohms or short replaces the inductor and capacitor. The general expression for average power is P is equal to VI cos theta of the voltage minus theta of the current, where theta of the voltage minus theta of the current is the angle between the voltage and the current, provided that the voltage and current are measured in RMS values. In the case of the current source, PCS is equal to 10 times 2 times cos 30 degrees, which works out to 17.32 watts. In order to calculate the average power delivered by the load source, we need the currents through the 1 ohm resistor. Using Kirchhoff's current law, IVS plus ISC, the current through the 1 ohm resistor, and that current is also equal to the voltage drop V1 across the 1 ohm resistor, divided by that 1 ohm resistor. Plugging in our known values, it's equal to V1 divided by 1 ohm, which equals 10 at 0 degree amps. We know the value of the current, ICS, because that is the current of the current source on the right-hand side of the circuit. So replacing ISC with 2 at 30 degrees, the equation now becomes IVS plus 2 at 30 degrees equals 10 at 0 degrees. Moving our known value to the right-hand side of the equation and keeping our one unknown quantity on the left, the current due to the voltage source, IVS, is equal to 10 at 0 degrees minus 2 at 30 degrees. Using rectangular coordinates in order to carry out the arithmetic subtraction on the right-hand side of the equation, we get 10 minus 1.7 plus j 1.0. That equals 8.3 minus j at 1.0, which equals 8.4 at minus 6.9 degree amps in polar coordinates. Using the formula for power once again, that is, P is equal to the RMS voltage times the RMS current times the angle between them, we know all of the required values now. So PVS is equal to 10 times 8.4 cos 0 degrees minus 6.9 degrees, which gives us 83.9 watts. Now, the total average power consumed is simply the arithmetic sum of the power supplied by the current source and the voltage source, which is the total power, PT, is equal to PCS plus PVS, which is 83.39 watts plus 17.32 watts, or 100.71 watts. And we're done. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. When it comes to residential power backup, EcoFlow offers a range of solutions suitable for everything from powering a single appliance during a short outage to running an entire home in the event of an extended blackout. You can have a look at all of these options that are available by simply going to this web address. Ready to go beyond just solving problems? If you've been following my daily posts and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available on my official course site, my stand store for electrical training. You can go to this website by tuning into the web address that you see at the bottom of this slide, https://stand.store/GVB.